In all the examples that we have discussed so far, we could find exact bound. We could find theta notation for the recurrences. There might be certain situations where it might not be possible to find the exact bound. And here is one example. Let's say we have this recurrence relation, Tn equal to Tn by 4 plus Tn by 2 plus Cn, and T1 is C. So if I break this using a normal recursion tree method, what will happen? I'll write the non-recursive part, then I'll write the recursive parts. Then I'll break it further. Non-recursive part of this is going to be Cn by 4. This is going to be Cn by 2. Then Tn by 16, Tn by 8, Tn by 8 and Tn by 4. And if I do the sum of these terms, I'll get 3 Cn by 4 here and Cn here. Now, if I do the sum of these 4 terms, I am going to get Cn by 16 plus Cn by 8 plus Cn by 8 plus Cn by 4. So this sum of these two is going to be Cn by 4, right? And sum of Cn by 4 plus Cn by 4 is going to be Cn by 2. And Cn by 16 plus Cn by 2 is going to be 9 Cn by 16, right? You might see a pattern now. It's a geometric progression with common ratio as 3 by 4, right? Cn, 3 Cn by 4, 9 Cn by 16. Now the problem here is all the leaves, they are not going to be at the same level. That's why this is special. That's why I said we are going to find an upper bound, right? So it's not going to be exact geometric progression till the bottom, right? It's going to be geometric progression up to certain points. Then this node will exhaust or finish first. You will see a leaf node very early here, and you will see a leaf node very late here in the last side, right? Why? Because we are reducing it by 4 here, 4, 16, then 64, and here we are reducing by 2. So 2, 4, 8, 16, right? And you will see somewhere in the middle here in the leaves. So here the leaf is going to be the topmost leaf, and it's going to be the bottommost leaf. It's going to be something like a tree where you have this at the very early and this at very late, and somewhere in the middle subtrees. So how do we find the exact bound? See, it's very difficult to find the exact bound. So what we do, we assume that the tree is full. We say we don't assume that there are we don't find the exact bound, right? We assume that the tree is full, and using this assumption we find a value and we say it's an upper bound, right? Because we are considering the tree to be full and we are calculating that value, and the actual value would be less than that because we are doing somewhere less work than this. So that's what I meant by upper bound. So what I do is I consider this geometric progression, right? The geometric progression is Cn plus 3 Cn by 4 plus 9 Cn by 16, right? And it's going to be go on like this. If I consider this tree as full, then how many terms the series would have? Basically, we need to find the depth of the rightmost leaf, right? And this is going to be reducing by 2, n equal to n by 2, n by 4 and so on. And we know the number of terms for that. It's theta of log n, right? We've done it multiple times. So there are theta log n terms in this series, right? And this series is a geometric progression. And the common ratio of this geometric progression is 3 by 4, right? It's less than 1. So one way is we find the exact value of this using the formula 1 minus r raised to the power n divided by 1 minus r. It's going to be complicated, right? What we can do is, we are anyways finding an upper bound, right? We can use big O and we can find the sum of infinite series. Because sum of infinite series with a common ratio less than 1 is very simple. It's a upon 1 minus r. So we are going to have Cn upon 1 minus 3 by 4, right? And this turns out to be big O of n only, right? Because these are just constants. So an upper bound on this recurrence is big O of n, right? So we could use recursion tree method to find an upper bound, and it's a good upper bound, right? Not bad upper bound, not like n square or n cube. We could find big O of n linear time upper bound on this recurrence relation. Here is one more example. We are going to use recursion tree method to find an upper bound. See, whenever you see a recurrence where one term is changing at a different speed and the other term is changing at a different speed, then you can get upper bound only using recursion tree method, right? Because doing exact computations might be difficult. So why are we getting upper bound here? See, if you draw the recursion tree of this, what will happen? It's changing, it's being reduced 1, 1, 1 at a time. It's reduced 2, 2, 2 at a time. So you will have a tree like this where this will be finished very fast, So you will have a tree where this leaf will be coming very early and this leaf will be coming very late, right? A tree like this you will have, right? So it will not be like a tree where every leaf is at the same level. This leaf is very high and this leaf is very low, right? So we can't find the exact bound, right? We can't do the exact sum here. We need, if we do, we need lots of more mathematics. It's difficult. So what are we going to do? We are going to consider this as a perfect tree and we are going to find an upper bound. So pause this video now and find an upper bound. So here is solution using recursion tree method. We have first written the non-recursive part, then recursive parts, then again non-recursive part and recursive parts, and then we did it again and we found the pattern that it's a geometric progression with common ratio 2. We are doing C work here, 2C here, 4C here, right? But the point is, it's not going to be a full tree. It's not going to be a geometric progression after certain terms. What will happen? This will finish very early and then you will have variations from the geometric progression, right? It won't be exact geometric progression, right? So it might happen after certain terms. It's not the double, right? It's less than double, then more less than double, and then it finishes slowly, right? So something like this is going to happen. So what we do here is we find an upper bound. We don't do the exact mathematics. We find an upper bound. We consider this as a full tree, right? And we say, okay, we can't do the exact analysis because it requires too much mathematics. We give you an upper bound. That's what recursion tree method claims. So what we do is we consider all n terms. We consider this geometric progression and put a big O notation here, right? Big O our friend, right? Whenever you don't know the exact bound, you use big O notation. And we have already discussed some of the series for n terms. It turns out to be 2 raised to the power n. Although in the earlier example we used theta notation, now we are using big O notation because it's an upper bound, right? We have used big O here, so we are using big O here as well.